Hello students, welcome to EPG Pathshala. I am Dr. Jaspreet Kaur and today we will study the module Biostatistics from the paper Human Growth, Development and Nutrition. Let us first look at the learning objectives of this module. By the end of this module, you will be able to define biostatistics and its scope, basic concepts in epidemiology, the applications of epidemiology, errors in epidemiological research, and explain the limitations of statistics. Human population can be studied without the compilation of data, which is always in the form of numbers. For these numbers to bring meaning for a better understanding of the population dynamics, some tool is required. This tool is called as statistics and it is the numerical representation of the facts and figures enabling meaningful interpretation and a validity with a scientific basis. The module would explain the meaning and scope of biostatistics, defining the epidemiology, scope and applications of epidemiology, disease transmissions and its dynamics, and errors in epidemiological research. Statistics and biostatistics. The word statistics come from the Greek word status, meaning a political state, and thus statistics in earlier days was mainly used for administering various affairs related to the state. For example, budgeting, taxing, the number of labor working in a factory, or considering the food requirements. Statistics are numerical statements of facts in any department of inquiry placed in relation to each other. This was a definition of statistics given by A. L. Bolle. However, this definition is incomplete as it does not take into account all the other aspects of statistics, which include analysis and interpretation. The most scientific definition of statistics was given by Croxton and Cowden, who defined statistics as the science of collection, presentation, analysis, and interpretation of numerical data from the logical analysis. Now, this definition clearly has four different stages, which include the first stage as the collection of data. Now, the data which is collected is entered and it is put to various statistical tools and then it is analyzed. So, the next stage becomes the analysis of data. Now, the analyzed data is interpreted and the last stage thus becomes the interpretation of data. Biostatistics. What is biostatistics? In simple terms, it means the branch dealing with the data relating to living organisms. It is the application of statistical methods to solving various medical, biological, and public health problems. The other term that is synonymously used with biostatistics is biometry. Now, statistics is an applied discipline, and though its roots lie in mathematics, the branch touches all the subjects of nutrition, medicine, biology, and public health. The fundamental of statistics as well as biostatistics lies on the concept of variation. Variation, what does it mean? It means that no two things in the universe are alike. Say, for example, we see a lot of variation in weight, height, across not only individuals but also populations. Similarly, the blood pressure of patients, their pulse rate, etc., also varies from person to person. It is not uniform or it is not same for every person. It is also useful in clinical trials where a scientist can see the effectiveness of certain drugs over a particular parameter. So, thus, biostatistics helps us to understand the relationship between certain disease and factors, to understand and enumerate the occurrence of various diseases, and lastly, it helps us understand the disease etiology. Now, biostatistics can be either descriptive or it can be inferential. Statistics is descriptive when the numerical data collected is presented in a tabular and pictorial forms and it expresses the nature of variable under study in terms of frequency, distribution, prediction equations, etc. Biostatistics is inferential when inferences are drawn for the entire population on the lot based on the sample. Now, the data which we collect from our fieldworks can be either in two forms. It can be either quantitative or qualitative. The quantitative data includes the measurements. The examples of quantitative data like height, weight, blood pressure, and pulse rate. These have a proper unit and thus they are called as quantitative data. The qualitative data, on the other hand, includes data like disease severity, the socioeconomic class, presence or absence of disease. The two types of data are subjected to various statistical methods that are specific to each kind, which means that we have different set of statistical tools which are used to analyze the quantitative and qualitative data. Now, these methods to treat these data, some of the examples are like average, correlation, regression, test of significance, t-test and f-test, etc. Whereas methods used to deal with qualitative data are like chi-square, order statistics, etc. Some of the tests which are frequently used in statistical inquiry are briefly explained in the text. So the data collected in a study is thus put to statistical analysis based on the aims and objectives and presented in a suitable format for further interpretation. Interpretation is an important factor since the figures obtained are influenced by a number of factors which can be correlated. After the preliminary evaluation of the results is done, one can further plan for detailed statistical analysis like ANOVA, test of significance between different populations or groups. Let us now look at some of the examples in biostatistics. Uh, Smoking, as we all know, causes cancer, but not everyone who smoke has cancer, and on the other hand, some people who never smoke have cancer. There is an element of uncertainty in this cause and effect element, which has to be appropriately addressed by studies investigating this effect. Now, in another example is in making designs for various health facilities, planners often need to consider the changes in the standards of care, demographic shifts, incorporation of new technologies. In another example, in studying the effect or pharmacokinetics of a new drug or a medicine, one needs to examine closely the changes in the levels of drug in the serum or blood over a defined period of time after giving a fixed dose. Now, any kind of individual variability, theoretical prediction, or measurement error can be harmful for the entire study and may not yield accurate results. Epidemiology. The word epidemiology is derived from the Greek words epi means upon and demos meaning people and logos means study. It is defined as the study of the distribution and determinants of health related states or events in specified populations and the application for this study to control of health problems. This definition was given by John M. Last in 1988. Hence, it is the study of the pattern of a particular disease in the population and the factors influencing this pattern. Epidemiologists are not only concerned with death or illness but also with improving the overall health status and means to improve health. Thus, we have the four objectives of epidemiology. These are it is a descriptive study of the health related state and its determinants in a given population. It is to describe the distribution and extent or magnitude of health and disease in a population. The second objective, analyze the major determinants and trace the natural history of a disease to understand how the disease spread and its course in individuals and groups. Third, the three E's. What are these three E's? That is efficiency, efficacy, and effectiveness of the methods to prevent, cure, and alleviate the disease. And lastly, evaluation of the process and outcome of services related to the above purposes. Let us discuss the applications of epidemiology. It is a useful tool in describing the health of a particular population group in terms of five major attributes, which includes measurement of the disease burden, trends in incidence and prevalence, studying any changes in the character of the disease, identifying special risk group, and lastly, to define the functional ability or the impairment. The second application is describing the natural history of the disease. That is, how the disease course and outcome of the disease in individuals and groups. This includes studying the complete etiology of the disease, its predisposing conditions and syndromes to prognosis of clinical progress of the disease. Thirdly, to understand the determinants of the disease, which could be ranging from genetic and environmental to infectious. It also includes further distinguishing between the association and determinants. Controlling and preventing the spread of the disease is another application of epidemiology, wherein it helps in identifying and removing the primary agent or the so-called determinant of the disease, protecting people from the agent, enhancing host resistance, these so-called protective mechanisms, and modifying the human behavior in order to minimize the risk and promote healthy actions among them. Planning and evaluating of the various health services for achieving better health status of the population or the group. The planning part includes estimating the needs and demands, locating major hazards or hindrances that could be easily avoided, and determining the supply of various resources. Basic measurements in epidemiology. Now, the basic fundamental practice often adopted in epidemiology is the measurement of health and disease or mortality and morbidity in human populations. There are various measurements that are frequently used by epidemiologists, and these include the measurements of mortality, morbidity, disability, natality, measurement of medical needs, healthcare facilities, utilization of health services, and other health-related events. Now, the three basic tools of measurements that are used frequently in epidemiology are the rates, ratios, and proportions. Let us discuss these one by one. Firstly, the rate. Rate, it measures the occurrence of some particular event in a population during a specified period of time. It is indicative of change in an event in a population in a given period of time. It comprises of four elements, which are the numerator, the denominator, time specification, and the multiplier. Now, the time here is usually a calendar year, and the rate is expressed per thousand or any other round figure, say for example 10,000 or 1 lakh, which is selected to avoid fractions. Now, these rates can be further of three types: crude rates, which are basically the actually observed rates without any modifications. Like, what are the examples of crude rates? This includes the birth rates and the death rates. Then they are called as crude birth rate or crude death rate. The next is the specific rates, which are also the actual observed rates, but here due to specific causes or specific time period. Like, for example, age sex groups, annual or weekly. And lastly, the standardized rates, which are derived out of direct or indirect standardization or are derived after adjustment. In this, the examples include the age and sex standardization rates. Next, we come to the ratio. Ratio is the measure of relation in size between two random quantities. Here we'll take up an example of the case fatality ratio. It is the total number of deaths due to a particular disease divided by the total number of cases due to same disease. So it means the case fatality rate is the measure of the severity of a disease in that particular population. Next is the proportion. Proportion expresses the relationship in magnitude of a part of the whole. That is, the numerator here is always a part of the denominator. Its unit is percent. For example, proportional mortality. Now, the proportional mortality rate for aged 60 years and above is the number of deaths of persons aged 60 plus years divided by the total deaths of all the age groups in that year. The proportional mortality is usually calculated for a broad disease group or when the population data are unavailable. Measures of disease frequency. There are several measures of disease frequency that are based on the fundamental concept of incidence and prevalence. It must be kept in mind that while calculating these measures, correct estimation of the number of people under consideration should be carefully selected. For example, while measuring the maternal morbidity rate, only women who had undergone pregnancy and delivery will be considered, and not all the women. When studying rates or ratios related to sexual health, only that proportion of the entire population which is sexually active should be considered, and not children or people above 60 years of age. Thus, a part of the population which is susceptible to a disease is called population at risk and is defined by various demographic, geographic, economic, or environmental factors. Incidence rate. Now, the incidence of a disease is defined as the number of new cases occurring in a specified period of time in a population at risk for developing the disease during that specified time. The incidence rate, we can calculate it with the help of a formula where I is the symbol for incidence and it is equal to the number of people who get a disease in a specified period divided by the sum of length of time during which each person in that population is at risk multiplied by 10 to the power n. The next is the prevalence rate, which is defined as the number of affected or diseased persons in a population at a specified time by the number of total persons in the population at that specified time. And it is denoted by the formula P is equal to number of people with the disease or condition in a specified time divided by the total number of people in the population at that specified time into 10 to the power n, where P denotes the prevalence rate. Let us look at the relationship between incidence and prevalence. Now, if the prevalence of a disease is low and does not vary over time, it can be prevalence is equal to incidence multiplied by the duration of the disease. However, it must be noted that the relationship between incidence and prevalence is always dynamic. While some advances in medicine may actually increase the prevalence of a disease, for example, medicines for heart problem may help to control the effects of the disease, resulting in lesser number of fatalities or deaths, but indirectly, more number of patients in the population are living with that disease, and hence the prevalence went up. Thus, studying the prevalence rates is helpful in designing policies related to the number of clinics based on the disease burden, the amount and type of rehab services, and the number of healthcare providers. Now, let me briefly explain you the difference between incidence and prevalence, and this I will explain on the basis of four parameters. The first is the numerator. In incidence, the number of new cases of disease during specified period of time, whereas in prevalence, the numerator is the number of existing cases of disease at a given point of time. The next parameter is the denominator. In incidence as well as in prevalence, both the denominator remains the same, which is population at risk. Next is the focus. Now in incidence, the focus is on whether the event is a new case and the time of onset of the disease. And in prevalence, the focus remains on presence or absence of a disease, and the time period here is arbitrary, rather a snapshot in time. The last parameter is the uses. In incidence, the uses are it expresses the risk of becoming ill, the main measure of acute diseases or conditions, but also used for chronic diseases. and it is more useful for studies of causation. Whereas in prevalence, the estimates the probability of the population being ill at the period of time being studied, and it is useful in the study of burden of chronic diseases and implication for health services. Dynamics of disease transmission. The communicable human diseases require certain prerequisites to transmit, and these include the agent, source for the agent, exit point from the agent, mode of transmission, entry point to the new agent, and a susceptible host. The source of infection is defined as the person, animal, object, or substance from which an infectious agent passes or is disseminated to the host. A reservoir is defined as any person, animal, arthropod, plant, soil, or substance, or a combination of these, in which an infectious agent lives and multiplies, on which it depends for survival, and where it reproduces itself in such a manner that it can be transmitted to a susceptible host. It is to be noted here that the reservoir and source may not always be the same or synonymous. The interaction of epidemiologic triad forms the basis of the disease transmission. The reservoir may be of three types. The first is the human reservoir. Man can be either a case or a carrier. A case is defined when a person in the population is identified as having a particular disease, health disorder, or condition which is under investigation, whereas a carrier is defined as an infected person or animal that harbors a specific infectious agent in the absence of discernible clinical disease and serves as a potential source of infection for others. The animal reservoir. Sometimes the source of infection may be animals or birds, and they can either be carriers or cases. The diseases caused by vertebrates are called zoonoses, for example, rabies, while birds can also spread some fatal illnesses among humans. The reservoir is a non-living thing, and this can include the soil, any inanimate thing that are reservoirs of infections. Let us discuss the errors in epidemiology. Now, the epidemiologists rely a great deal on the measurement, and one of the objectives of epidemiology is to provide accurate measures of disease occurrence and its outcome. There may be many possibilities of errors in measurements which must be recognized in order to try for its best possible elimination. Now, the errors in epidemiology may be classified into two types, the random or systematic. Random errors occur when the value of the sample deviates from that of the true population value due to chance alone. There are three major sources of random errors, which include individual biological variation, sampling error, and measurement error. In addition to this, random errors can never be completely eliminated because we study only a sample of the population rather than the population itself. This error can be, however, reduced only by increasing the sample size. Higher the sample size, lesser the random error. Other ways which can be used to reduce the random error is by minimizing on the individual measurement, which can be achieved by following strict protocols. It should be made mandatory for every investigator to undergo a stipulated training period before actually taking the measurements. Further, the laboratories should have proper documentation instruments, and they should be able to measure the accuracy and precision of their instruments. By increasing the sample size of the study, group, or population, we thereby increase the statistical power to further detect the differences. Sample size should be carefully worked out based on fixed statistical formulas, which again vary as per the requirements of the study. However, in practice, small size is often affected by the logistic and financial constraints. The next is the systematic errors, which occurs when results differ in a systematic manner from the true values. Unlike the random errors, systematic errors are not affected by sample size, and a study with a small systematic error is said to have high accuracy. There are more than 30 types of systematic errors that have been identified in epidemiology, but the principal ones are selection bias and measurement or classification bias. The former occurs when there is a systematic error in the characteristics of the sample selected and the people who are not a part of the study. A selection bias occurs when there is unavailability of the people for the study of a particular disease or factor. Such examples are frequently encountered in studying the effect of occupation on the health of individuals. In such cases, employees who are healthy enough to perform their duties should be selected in the sample, but this usually does not happen, leading to selection bias. Individuals who are already ill or cannot perform their duties effectively introduce a selection bias to the study. On the other hand, measurement bias occurs due to personal negligence. It occurs when an individual does not measure accurately what he is supposed to measure. Here, the varying perception and understanding may also affect the way in which measurements are taken. This error may occur at the level of the investigator or at the respondent level. For example, in retrospective case control studies, there is a recall bias wherein an individual may find it difficult to recall some past exposure, thus affecting the results for the entire study. Such biases can result in over-reporting as well as under-reporting of the cases. Further, if the investigator is already aware of the exposure status of the individual in the study, it may lead to observer bias. Such bias is removed by conducting a blind or double-blind study where the investigator do not know how the participants are classified. A double-blind study means wherein neither the investigator nor the participant knows how the latter are classified. Limitations of statistics or biostatistics. Now, besides its wide use in a variety of subjects and fields, as well as public health, statistics and biostatistics has certain limitations. And what are these limitations? Statistics is applicable only to an aggregation of data rather than individual data. It can help interpret results on a large group or population level rather than giving us results for an individual level. For example, it can give us the result for income of a group or population, but not the per capita income of the individual. Further, it describes numerical information of the numerical data. It cannot give us an estimate of the level of honesty, hatred, love, intelligence, or beauty, as no statistical test can be directly applied to measure these variables. However, statistics can be applied to these variables only after converting them into measurable quantitative traits. Statistical laws are ever changing, and our statistical conclusions are not universally true. Statistics, if used by amateurs, can prove to be very dangerous as it may lead to wrong conclusions. Thus, proper and scientific knowledge of statistics is of utmost importance before one can use it to interpret large quantity data. As King says aptly, statistics is like clay of which one can make a god or devil as one pleases. And lastly, the statistics does not provide complete solution to the problems which may be beyond the realm of its field of inquiry. For example, a problem with statistical solution may be affected by the non-quantifiable characteristics such as culture, economy, religious idols of the country or individuals. Now let us sum up what we have learned so far in this module. Biostatistics is the application of statistics to solution of medical, biological, and public health problems synonymously used with biometry. Epidemiology is the study of disease pattern in a population and what affects or determines this pattern. Now, there are three aspects of morbidity which are commonly used by epidemiologists, which are rates, ratio, and proportion. Disease frequency is a measure of prevalence and incidence which are used to describe the magnitude of a disease in a given population at a particular point of time. Epidemiology is readily applied in describing the health of a population, describing its natural history, finding the determinants of the disease, control and prevention of disease, and planning and evaluating the existing health services. Communicable human disease require certain prerequisites to transmit, and these include the agent, source for agent, exit point from the agent, mode of transmission, entry point to the new agent, and a susceptible host. Communicable disease can be transmitted either directly, that is from human to human, or indirectly, which can be via a vector or vehicle. Now, there can be two types of errors in epidemiology: random and systematic. Random errors can be caused by individual biological variation, sampling error, and measurement error, whereas the systematic errors are caused by selection and measurement bias. Besides its wide use in a variety of subjects and fields, as well as public health, statistics and biostatistics has certain limitations. It is applicable only to an aggregation of data, describes numerical information, statistical laws are ever changing, and it does not provide a complete solution to the problems.